is on ratio and proportion. Now, how does ratio and proportion feature in geometry? Well, what is a ratio? A ratio is an easy thing, isn't it so? A ratio is just comparing two quantities, isn't it so? Just comparing. We get a proportion when we say there is a proportion and we link up two ratios and we equate them, then we've got what is called a proportionality statement. So, what do we say? How do we use the word ratio? We say the ratio of teachers to learners, right, in the schools that you are most probably going to teach, would be about 1:50. Maybe in some of the classes there will be 50 learners and you will be teaching them. So the ratio of teachers to learners will be 1:50. And that immediately produces an equation. What is the equation? Doesn't that produce an equation? Because I said, look what I said. I said the ratio of teachers to learners equals 1:50. Where's the equation? There must be an equation there. What's the equation? Would you find an equal sign somewhere in what I said? Is there an equal sign in what I said? The ratio of teachers to learners equals 1:50. So you got the equal sign. It's a question of what do you put on the left of the equal sign, what do you put on the right. Okay, I'm starting I read from left to right, right? Like all of you, I think. So the ratio of teachers to learners equals 1:50. So when I write that, how will I write? How do you write ratios? It's 2 with that little colon. Let's write it as fractions, because ratio is a fraction, isn't it? And ratio is fractions. 1:2 is same as 1/2, isn't it? So let's write it like that. So assuming we use the letter T for teachers and L for learners, then what will I write? T over L equals what? 1/50. So you're going to solve the equation, isn't it? So whenever you talk about a ratio and you make a comparison between quantities, you've got to solve the equation. And as long as we got equation, we got answer. Right? Isn't it so? So we can start solving things, finding x's and so on and that sort of a thing. So now we're going to bring that into our geometry. How do we bring that into the geometry? Well, the first theorem is there. I'm going to talk through the geometry because I want you to work through things. Now, watch, there is the diagram there on the board and it's in front of you as well. If you've got any ordinary triangle, and what is wrong there? Just any triangle, and you've got a line DE. Let me show it to you here, right? DE, you can put D anywhere, right? Right at the top here and E, and if you draw that line parallel, to one of the sides, in that case DE is drawn parallel to B side, then immediately what it does is it cuts the other two sides proportionally. Now we're going to understand what that means. What does it mean that if you draw a line parallel to one side of a triangle, it divides the other two sides proportionally? That's what the theorem says. What is the meaning of that? Now, if you don't have the meaning, you won't be able to use it. So get the meaning carefully, watch. It's not something very complicated. If it divides the other two sides proportionally, that means the ratio of this part to that part there, that means the AD to DB, would be the same as AE to EC. Just like I told you now, the ratio of teachers to learners is 1/50. The ratio of AD to DB is AE over AC, so is AE to AC, EC rather. So I can make an equation like this, right? So whenever DE is parallel to BC, we will have the following equation. AD over DB is equal to AE over EC. That's a very simple thing, isn't it? Very simple to understand. Whenever you have a line parallel to one side of a triangle, immediately you have yourself an equation like this. Right. Now, we usually change that around. We change that around and we normally don't like DB. Why is DB not the most convenient side to work with? Any reason? Well, it's not a big reason, it's nothing profound. The reason is that DB doesn't belong to a triangle. How many triangles in the diagram? How many triangles? Only two triangles, no more than two triangles. The small one, AE, and the big one. Now DB doesn't belong, it's not a side of any particular triangle. It is a side of a trapezium globe, but not the side of any triangle. So what we like to do is link it up to triangle. So AD is the side of the triangle and AB is. So we like to rather have something as AD over AB equals AE over AC, then all those four line segments are sides of triangles, isn't it? And so we do that very easily actually. Oh, I don't know, I've got it a little lower down. Oh, before that I've got an example here, right? Let's get to understand this example. In other words, if we know, for example, that AD is 3, and DB is 2, and EC is 4, and we only don't know that, can we solve for it? Yes, we can. Why? We'll just put it in here. We can put the AD, which was what? 3, and we'll put the DB, which was 2, and we'll put in, we don't know the AE, we'll put in the EC to be 4, and we've got everything but 1, and we can solve it. Is that right? So that's one of the easiest and the most elementary applications that comes out to 6. But here's another useful fact. And it's not so clear here, but you can read in yours. That what we do with this triangle, we want to bring in a side of a triangle. What we want to do. Yes.
Can you please go down
The first one. Yes.
Yeah, so I'm saying like if you try to explain this to students, what if they make a mistake of saying AD over AB? Like how can we try to avoid that? Because it might happen. Like at this game, while you're saying AD over DB, because sometimes it can happen that a student would just be like AD over AD.
Well, actually, that would be right too. It only depends on what you write on the other side. That's what I'm coming to demonstrate to you just now. But you see, we didn't prove this theorem. The only reason we start the theorem like this, AD over DB, is because that's the easiest one to prove. Right? It's the easiest to prove that. And that's besides, maybe I should give you some hints on proof. How would we prove this? Right? I don't want to dwell too much on the proof because I'd like you to apply and be able to solve problems. How would we prove that AD over DB is equal to AE over EC? Now, those of you who have some idea of these pictures would be able to see, if I draw this line here, right? If I draw that line there, then I'll have a triangle here and a triangle there. Isn't it? And if I have those two triangles, I'm just getting you to imagine, right? It's just a hint for you when you're looking at the proof, it wouldn't be too hard to. Then the areas of triangles are half base times height, isn't it? Everybody knows that. So if this is the base for this triangle and this is the base for the other smaller triangle, then the area of this triangle will be this base times the height. And the area of this triangle, small one, will be dB times the height. But the height will be the same, isn't it? Isn't it? So if you put one area over the other area, the halves will cancel, the heights will cancel, and all you'll have is AD over dB, and you'll have a nice answer for it. And similarly, if you draw that line there, and you do the same for the other side, you'll have an AE over, well, you wouldn't get EC immediately, and then of course you'll have to show two more triangles are equal in area, and maybe I'll demonstrate that just now on the right on the board. It's terrible to talk like this without writing anything. But anyhow, I just was trying to give you an idea, it's very easy to prove this. So that is why we do this. But the more useful thing is what you are talking about. Supposing we wanted to say AD over AB, how would we do it? What answer would we have? Well, that's what I was going to write just now. So let's see, what have I got there? Let's put this picture up a bit. So, if I said at the moment all I'm telling you is that it's AD over DB is equal to AE over EC. And then I said it's the easiest thing to prove, right? Of all the things that we want to prove about ratios. But now Montreux says, why don't we say, or not why don't we, if somebody makes a mistake, but that wouldn't be a bad mistake unless, it wouldn't be a mistake at all, depending on what they write on the other side. AD over AB, in other words, they take the whole long line, which is sort of makes sense, isn't it so? The long line makes sense. It's not AB because it's the side of a triangle. The question is, what are they going to write on this side? If they write that, they would obviously be wrong, isn't it? Yeah. So what should they write? They should rather write AE over AC, and then they would be perfectly right. How do you know that? How do you know they'll be perfectly good? Because this is a nice property of ratios. And you can prove it. It's really nice to prove. So let me write it. These are benign dual triangles. This is property of the ratio. Now, if somebody tells you that A over B is equal to C over D, somebody tells you that. In other words, that's a fact. Then what you can conclude from there is there are many things you can conclude. One of the things that you can conclude is that A over A plus B is equal to C over C plus D. You believe that? You don't believe it? Well, okay, it's easy to prove. Maybe I can just demonstrate the proof just now. But before that, why don't you test it with some numbers? Right? Let's say 1 over 2. Always test. Every time you doubt something, just go and check it out and see whether it actually works. 1 over 2 is the same as 3 over 6. Is that right? 3 over 6. Now, if we had to perform this little thing on that, what would we get? 1 over, in other words, we do the A over A plus B. 1 over? Oh, sorry, what is this? Oh, sorry. I'm not looking at it. That's one of the disadvantages of looking here, because I think I can see what you are telling me. So just tell me to bring it down. Don't feel awkward about that, because it's pointless my asking you a question and you just look at me because you can't see. Not going to be very useful, isn't it? So I've got 1 over 2 is equal to 3 over 6. That's true. Is that true? Now, I want to do what I did here, because I claimed just now that if somebody tells you A over B is equal to C over D, then you can tell them that A over A plus B is equal to C over C plus D. What can you write here to show this? 1 over 1 plus 2, which is 3. 1 over 1 plus 2 must equal, that's what we're checking out, 3 over 3 plus 6. Is that true? Check it out. What do you get? 1 over 3 is equal to 3 over 9. Are they the same? Yeah. So what? If you do a crazy thing like that, you take the numerator and put it over numerator plus denominator, and if you do it on both sides, it works. But that's only one example, isn't it? What if it doesn't work at other things? Charles, you must have come across many of these proofs and solutions that children give that they make a double mistake and they get it right. But this is not a hard to prove at all. You can prove it and I'll give you a hint, right? The way to do it is like this. This is what you want to prove. Isn't this the required to prove? Let's see if you can see this. Required to prove is this, right? Required to prove is that. Given is this. That's given and that's what you want to prove, right? So I'll give you a hint and you can check it out. So you really want to prove that A over B, A over A plus B is equal to C over C plus D. All you do is you let either of these ratios or both rather, let A over B equal say something like K. Right? Well, if A over B is equal to K, then C over D is also equal. Because that's what's given. A over B is equal to C over D. So if A over B is equal to K, then C over D is also equal to K. And from there, what can you get? You can get that A is equal to BK. And also C is equal to DK. Would that be true? A is equal to B times K, C is equal to D times K. Now that's what came from the given. If you just substitute that in there for the A's and substitute that in there for the C's, all the K's will cancel out and you'll end up with what you got here. Or rather still, you'll end up with something for the left-hand side and you'll end up with the same thing for the right-hand side. In other words, if you take the left-hand side of the required to prove, which is A over A plus B, and you go and substitute for the A in there, you'll get an answer, right? And then, if you do the same for the right-hand side, C over C plus D, you'll get the same answer there, and you will have a proof, if you want to prove. Of course, I know you math students will want to prove, right? So, but I'm not going to dwell too much on that. There are many such laws you can create. In other words, it's actually true that A over A minus B is equal to C over C minus B. That's true as well. But there are many laws of these ratios, and every time you want to prove it, the method is always the same, so if you run into it. Okay, so I'm not going to dwell too much on that. Let's spoil the geometry for today, right? That's the algebra, and you got to know it too. See, most things, not most things, everything in maths that you come across, you might always find a student who would ask you, but how do you know that that's true? So you've got to develop the art of proof. In other words, you must be able to convince them. The majority of children in your class won't necessarily want to be convinced about many things, because they obviously won't be the students who want to go and study mathematics in any big way. But it's good to encourage children to ask why, and to ask for the proof, because if there is a potential mathematics student in your class or a potential mathematician, then they'll ask these questions, and you must not deny them the opportunity of actually seeing the proof. So, that's a theorem. So we got the theorem in our heads, right? We're going to do the application just now. The converse will obviously, the converse isn't. What will the converse say of a theorem like this? The original theorem says if a line is drawn parallel to one side of a triangle, it will divide the other two sides proportionally. What does that mean? See, that is why I write it in terms that are useful to us. Look, what did I write here? I wrote DE parallel to BC implies that AD over DB is equal to AE over AC, because the words, a line drawn parallel to one side of the triangle divides the other two sides proportionally, must be known. And we must be able to speak in English and say, or the way, whichever way we speak, state the theorem. That's a statement. But that must mean something, isn't it? In the context of a diagram. And so we've got a diagram, and in this diagram, what does the theorem mean? It means that if DE is drawn parallel to BC in this triangle ABC like that, then AD over DB is equal to AE over EC, then we can use it. Just the English expression of it is not very useful. Now, what do you think will be the converse? The converse will say, if AE over DB is equal, I don't know what I want to say the last time, sorry, I'm really missing things today. But let's get the converse right. If in a triangle you've got these 2 points D and E in such a way that AD over DB turns out to be the same as AE over EC, then you'll conclude what? That line DE must have been parallel. That will be the converse. But I went off at a tangent telling you all about that proportion, but I didn't complete what I wanted to tell you. What I wanted to tell you is that because that, in other words, to answer Nonto's question, and Nonto's question was, if somebody wrote AE over AB, then they can happily write, was it AD? AD over AB, then they can happily write AE over AC, and the basis for that would be what? We already believe that AE over EB is equal to AD over, that's fine. AE over what was it? EB. Sorry. Are you right?
The diagram?
Oh no, I have the diagram here, but I just want somewhere to write. So A over AD is equal to, let me write it all over again. AD over AB is equal to AE over AC. Right. Now, this is what we want to establish. This is the fact we want to establish, right? What do we know? I wrote the same thing again, but anyhow, maybe I'm not clearing down. Maybe if I let the diagram, I'll tell you. See, let's watch the diagram first, right? So what we have is this statement. What do I want is AD over AB is equal to AE over AC. How would I get that? So let me just show you how I would get that. So, you see, I know this AE over AC is equal to AD over AB, right? So what I do is I take the AD, like I did the last time, and say AD plus AB. I keep writing the one that I want rather than the one that I have. I'd rather give it up. DB and AE over EC. Right? So, now it's asked to go to that. So this is what I have. This is a given because I said I'm going to prove it and I'm going to be proving it. That's what the theorem says. So I'll have AD over AD plus DB must equal AE over AE plus EC. And that is what? That's the same as AD over AD plus DB. If you look at the diagram, AD plus DB, what is it? What is AD plus DB? In the diagram. If you take the AD and you add it to DB, what do you get? The whole of AD. All of AD. And on this side, if you take the AE and you add it to the EC, what will you get? AC. So in other words, now you've established. In other words, we use that simple fact that I told you, that if two numbers A over B are in a ratio such that it's equal to C over D, then A over A plus B is equal to C over C plus D. Right? So I use that fact, which is very provable, to make such a conclusion. And that's what's written here in this colored thing here. It turns out more useful since all four sides of the equation of a triangle, if you write it like that, AD over AD is equal to AE over AC. So to finally answer your question, you can write AE over AD over AB, provided on the right hand side you write AE over AC. Right. But it's actually the more useful case, as you will see a little while from now. Okay, now we've settled the converse and we've settled the theorem. So you know two facts. Now on the basis of those facts, let's see how many of those problems you can solve. So fire away with it quickly. The application. Or maybe I should just do a bit more demonstration. I don't have I have a pen. I just need I like to do these things because just wait a minute, because I just wanted to demonstrate, because teaching strategies, I hate for you to do things the way I'm doing it here with you with children, because you see, we taught them a theorem, right? We taught them a theorem, or two theorems. We taught them this theorem here. And they must get quick ways of seeing that of understanding it. And what would be a quick way? Well, we'll see what we've done there. We just drew a triangle there, and we drew a line parallel, just parallel anyway, right? So we've got A, B, C, D, and E. And immediately we asked them, okay, what can you say? Well, it's much faster to use small letters like A, B, E and F. And we say, what can you conclude from a diagram like that? And immediately what must they say? They must say that A over B, small letter A, over small letter B, must equal small letter E over small letter F. Why? Because those lines are parallel. And so it's always useful to have many, many diagrams like that. So these two lines are parallel, and I'll call that X, Y, C and D, and what's the conclusion there? X over Y is equal to, I wrote the X in the way I'm looking at it, X over Y must equal C over D. Any other shape that you might write it in, a triangle like that, and you can have a long line like that, but as long as this is parallel to that, and you got 5, 2, and you got 10 there, it doesn't look right, what must that be? It's very easy to tell. Let's call it X. And what will be the equation immediately if these two lines are parallel? 5, alright, 2 over 5 over 2 is equal to 10 over X. You see now, in other words, what are you doing in this method by repeating with a large number of diagrams? You are getting them to apply the theorems in its simplest form. In its simplest form, you are getting them to apply the theorem. So once they've mastered that, it's not as simple as you think for children who are 15 and 16 years old or 17, until they've seen it several times. And once they've mastered that, then they're ready to go and do an application. And what I normally would do if I'm working with young children, I would tell them, okay, here it is. Give me the ratio here, and I'll draw that there, and I'll say that that is X, and that is Y, and that is P, and that is Q. And what's the ratio? Yes? X over Y is equal to P over Q. And I will tell them that that's wrong. Why? Because I said nothing about those two lines being parallel. Isn't it? I said nothing at all. So, well, of course that's what I meant. I may have forgotten to put that, but unless I write that they are parallel or indicate that they are parallel, that theorem would not hold. And so would the converse. Now fire up with those few problems and let's see if you can just get a hang of it. You just got one page of problems on this. Well, the first one is done. So there's nothing for you to do except to read it. In triangle PQRST is parallel to QR. Therefore, immediately PS over PQ, sorry, what's it? PS over SQ is equal to PT over TR, or look what I've written there. PS over the whole line PQ is equal to PT over the whole line PR. Can you see that? This one, is it? Yeah. So, PS over the whole line PQ is the same as PT over the whole line PR. So that there's nothing more to do. That's just a fact. You're going to fill in for number 2, and for number 3 is also done for you to look at, and number 4 for you to write an answer. And then for number 5 for you to draw a conclusion, and number 6 to calculate X, and number 7 to make some calculations, the length of AC, and number 8, the length of PQ. Well, as you can see, the main ones will come in number 6, 7, and 8. So rush through the first ones. You can see AF is 12, and you've got pairs of parallel lines. Now, Helen. Now, as soon as you got that, you've got to sort out your triangle. And what is nice is to do this if you are teaching it to children, is to actually do it on Sketchpad or on GeoGebra, then you can delete. You see what's happened here? There's too many lines that's messing everything up. So let's take them part at a time. So over here we've got 15, 10, we've got 12. It's possible to find this. So this is a bit of a nuisance. So let's get it out of the way, take it out. And let's take that out. Right? So pretend that doesn't exist. Now do you see an easy triangle? If you remove all those green lines that I made, you see an easy triangle. You see a triangle like EAB, that triangle there, right? Maybe I should just shade it up so that you'll be able to see it. Maybe I shouldn't have put the green like that, but assuming I shade it up like that, then you can see that's your main triangle, and there's a line drawn parallel to one side of that triangle, and immediately you've got 15 over 10 must equal to 12 over FE, and you can work out FE. Can you see that? Right, so you got FE, and what was it? What was it? Anybody worked it out?
8.
How many? 8. Yeah, because you want the ratio of 3 over 2. So that's 8. And now comes the next thing. What do they want after that? Oh, they want EC again. So that means you want the EC. So to get the EC, you now can take the big triangle, and that line there is parallel to that line. So immediately you can see that 15 over 10 would have to be this whole thing, 20 over EC. And then you're done. Isn't it? 15 over 10 is equal to 20 over EC. And you can solve for EC. Right, which is 200 over 15. Okay? And this one here, well, this is bringing more geometry into the picture. In all these problems, what's going to happen, you'll see just now when we're doing the next topic, we're going to bring in all the geometry that we've ever done in the last few weeks. In other words, the geometry starting from grade 8 geometry relative to grade 11 geometry, and we're going to apply it all at one go. So in this particular shape here, triangle PQ, in that triangle, TS is parallel to PQ, as you can see there. QT bisects, these two angles are equal. Now, whenever you get angles in a problem like this, but this theorem had nothing to do with angles, isn't it? The theorem said a line drawn parallel to one side of the triangle will divide the other two sides proportionally. Where's angles? No angles come into the picture. But you see, in maths we do that because you know all about angles, so why don't we make two angles there equal? And then what do you think of? You got parallel lines. And when you got parallel lines, you'll have alternate angles that are equal, corresponding angles that are equal, and coordinate angles that are supplementary. And so immediately what can you do? There's an X here, look for the alternate angles, that one there, can you see what I'm writing? That one there is alternate to that angle there, so that one must be X. Right? Because these two lines are parallel. Oh, as soon as I see that, then I see an X here as well, so what kind of a triangle do I see? Isosceles triangle. What's special about an isosceles triangle? There'll be two sides equal, which means this part here will equal that part there. Can you see all the mathematics comes up now? Which has got little to do with our theorem so far. The theorem taught us that if a line is drawn parallel to one side of a triangle, divide the other two sides proportionally. Now let's see how all that comes into play, or is it of any use. TR is given to be 9, well, that's written there, everything is written there. And the question was find PQ, but that's rather easy because you didn't have to find PQ. What did you find instead? You can find what you can find. And what you can find is PT. And if you can find PT, then you didn't have to worry about finding PQY. Because PQ was the same as PT. You see that? So what was PT? What was it? 12. So PT was 12, and because these two are equal, that must be 12. You see the method by which we go and solve a problem. We solve it using old information that we've covered before. Anyhow, that's so much for that. Now, can we pass on the second